Okay, so uh, just like with the first exam, the plan is to talk briefly logistics, then take any immediate questions. If there aren't any, then I'll just jump into recapping the notes. And then after that, again, just any questions that are left over. So feel free to ask questions as I'm going over the notes as well. So logistically, for this exam, it's very similar to the first. You can have a cheat sheet with the front of an 8.5 by 11 sheet of paper with whatever you want on it. I would recommend certain things, maybe like having not necessarily specific examples, more like having kind of a step by step, like to solve this type of problem, do these steps. And then you could have one example to show those steps, but I wouldn't rely so much on a specific example because you can kind of get stuck that way if you rely too heavy on the cheat sheet. Um, the length of the exam, I don't know yet. It still is being written, but it should be similar to the first one, and it will probably skew similarly with conceptual versus calculation. Usually it's about 1/3 to maybe 40% conceptual, and then the rest is calculation. So that is the main things I can think of logistics wise. So here I'll just answer any kind of burning questions. So it can be from the practice exam, it can be from anything. I just want to address any immediate questions first.
Yeah, I have a question about on the practice exam, question number 4.
Okay. All right.
So what I have problems with is when I see questions like this where I have to make a free body diagram, I don't know where to start or how some of this where the arrows go and whatnot.
Okay. So um, free body diagrams, the general process is your first step is figure out what it is you want a free body diagram for. So here it's pretty clear it's going to be for that block, but sometimes it's not as clear and you have to choose. Um, so it could be person, car, whatever the object of interest is. Then you draw the forces acting on the object. I usually like to do that before actually making the real free body diagram. So if I'm told that a car is on a hill, for instance, then I might first sketch a car on a hill. And being able to draw in something, stylus is, oh, that crashed. 1 second. Being able to draw in something quickly to address the problem that's being asked is a really good thing to start really any problem with, is just a quick sketch. So I would draw the car on the hill and think about the forces acting on it. And that would be if I can think of anything that the car is interacting with, that's a possibility for a force. So the car is interacting with this hill right now, it's sitting on it. And so the forces involved would be if the car is just sitting here, it's got friction keeping it from sliding down the hill, be static friction. The hill is also keeping it from falling through its surface. That's where the normal force comes from, is it's what's preventing the car from falling down this way. Then the one that I can't see in the picture, but I know is there, is the whole earth. And that's where the weight of the car comes from. And that is already about halfway to a free body diagram. The rest is just um, choose convenient axes. So we isolate, I make that car into just a dot just because I don't really care about the physical features of it as far as how it looks. I just care about the forces on it. And so a dot kind of abstracts away all the unnecessary information about the car. So I got the normal force, I've got friction, I've got weight, mg. And so I would choose axes. Convenient axes would be ones where I don't have to find a lot of components. I don't have to do a lot of sine and cosine stuff. And so that's why we tend to choose them this way for stuff on a hill, because then I only have to do sine and cosine for one thing. Then the last major step is break any forces that aren't along an axis into components. So mg, the weight, is the only one that's not sitting on either axis. And so I need to think about how much of it sits along one and how much of it sits along the other. And that's the parallelogram way of looking at a vector, is those two green vectors add together to give the actual weight. They are the components of that weight vector. And to decide whether I'm using sine or cosine just depends on the situation. So in my original picture, if the angle of the hill is theta, this angle right here also ends up being theta. So I'll transfer that over here. And then I know whether I use sine or cosine. That's about where it starts to become problem specific, but those are really common steps to any problem with a free body diagram. So to answer this specific question, we don't actually need to go too deep into free body diagrams. We just need to think more about that if you have two forces in the same direction, that's best case scenario as far as getting a large net force out. One thing to think about is like if you're trying to pull a tree stump out of the ground or something, you got something, you want to yank it out of there and you got a friend to help you. You don't want to both be fighting against each other by pulling on either side of it. That's probably the worst way to get it out of the ground. It may be a little better if, maybe we're talking about like you got a truck and you got a tow hitch on it to do this, but it's better if you pull on the same side. That's going to give you the largest possible net force. So Newton's second law relates that net force to the acceleration. It says your acceleration is going to be whatever the net force is over the mass. And if I cut out, I was having that problem yesterday, please let me know and I'll repeat anything. Let me go ahead and that's if I can do anything about internet connection. All right. So with that in mind, which one do you think is going to give us the largest acceleration?
4.
Yeah. So why do you think 4?
Because they're both going the same way.
Yeah. So that's going to be the best possible way to pull that stump out of the ground, is if you're both pulling on the same side. Number 1 would be the worst way, and you're going to get the least acceleration. So if I were ranking most to least acceleration, 4 would be first. Then let's see. 3 would be next best because they're still somewhat in the same direction. Then 2, because they're perpendicular. Then number 5, because now they're pointing someone in opposite directions. And then number 1 is the worst way because they're pointing in exact opposite directions. Does that all make sense?
Yes, sir.
Okay. All right. Other questions? Okay. Well, if there's not immediate ones, I'll just maybe say some things about the notes. So I think it's probably pretty clear that any conceptual stuff is going to be relating to what Newton's laws say. So it is, if they're not ingrained at this point, if they're not burned in, which they may not be, they're a good thing to write down on a cheat sheet. So you remember what each one says, and then maybe you could make a few notes about any consequences of them that we've seen. So the first law is about inertia. It's that stuff keeps doing what it was doing unless something acts to change that. Stuff likes to keep doing or keep moving the way it is currently moving. If it's not moving, it likes to keep doing that. If it is moving, it likes to keep doing it exactly the same way, same speed, same direction. Unless that something that acts is a non-zero net force. So some terms to look out for when you're dealing with calculation problems are things like constant velocity. Usually it's pretty obvious to us that rest means that the net force is zero and the acceleration is zero. So in our approach to talking about applying Newton's laws to solving problems, we usually say, okay, find the net force in the x direction and the net force in the y direction and set both equal to mass times their respective accelerations, and then decide whether an acceleration is actually happening. So this would be, if you see something's at rest, you can say the accelerations are zero. But if you see something is moving at constant velocity, you can still say that. The only case in which something does not have a zero acceleration is when it is speeding up, slowing down, or changing direction. So constant velocity is just forgotten a lot of the time. Yet one more way it could be worded is that something is in equilibrium. That is pretty much by definition that the net force on it is zero and the acceleration is zero. So all of those are, in the sense of solving problems, equivalent statements. And it's good to know that as you read the problems. Inertial reference frames, not on there. The second law says what happens when you do have a net force acting. First law is saying, I can tell you for sure what's going to happen as long as there is no net force. Second law says, oh, there is a net force now. Here's what happens. And what happens is the acceleration you get as a result of that net force is proportional to the net force and inversely proportional to mass. Okay, problem 49 and 47. Yeah, here, by the way, Obi is like the actual step-by-step. When we first introduced free body diagrams, it may give more details than I gave before. But yeah, let me pivot over to 49 and 47. Okay, so if you got the speed of the satellite, then 47 becomes a little bit easier. So for the speed, that's where we came up with this expression. And that expression comes from that gravity is acting as the only force on the satellite, and it is acting towards, in this case, Mars. This is the general expression for the gravitational force, and it's acting as a centripetal force, so we can set it equal to mass times centripetal acceleration. You solve that for V, you get what I wrote over on the left. So you apply that equation, that will give you 46. Then, once you know that information, 47, you can just remember that that speed can also be written as circumference over period, the time it takes for one orbit. And so the period is 2 pi r over that speed. If you wanted to do it in one shot without doing number 46 first, you would just sub in all of this stuff right here for V. And what comes out as a result is this 2 pi r to the 3/2 over square root g times, in this case, the mass of Mars. And r would be not the radius of Mars, but that plus this altitude, because the satellite is not on the surface of Mars. It's there, and then this additional distance, which is, they call it the altitude above straight H. Those together is what you use for little r. Do you want more detail on that one, Austin, or do you want me to jump to 49? It's kind of up to you. Do you need more detail on this one? Okay. All right, so 49. Um, we've got a car heading towards us as it travels around a circular track of radius 24 meters. If I didn't have a picture like this already drawn, I'd be drawing it right now. So I'm given a radius, and this is another tip, is underline anything you're given, and if we have a symbol we pretty much always use for it, write that symbol there, because that's going to help you narrow down which equations could be relevant. So coefficient of static friction, 0.6. We use mu s for that. What speed? Speed is v, and it's saying what is it? So this is the thing it's asking us about. On the verge of sliding out of the circle. This is another kind of buzzword. On the verge of sliding, on the verge of slipping, about to slip, things like that are saying you are looking at maximum static friction. Because anything more, and you will be dealing with kinetic friction. So, last thing I might notice is if it's a circular track, we're dealing with circular motion, and so centripetal forces, centripetal accelerations. And that all gives me everything I need to answer this question. I think about what forces are acting on the car. Normal force from the road, the weight of the car, and in this case, friction acts towards the center, and it is at its maximum value. It acts towards the center because it's the thing letting the car get around the turn. It is the centripetal force. If I'm looking at the car from the front, my free body diagram looks like this. And on problems on the exam, if it's involving forces, a lot of them will say you have to draw a free body diagram. It's part of the credit for the problem. So it is good to be practicing those. So this is my free body diagram. For centripetal motion problems, I usually also like to label the direction of the centripetal acceleration. It's going to be the same as the direction of whatever the force acting centripetally is, in this case friction, and then I'll just note it over on my free body diagram. It's not a force, so it isn't technically part of the free body diagram, but I can at least remember which way it's pointing. So in the x direction, I've just got friction. If I'm calling left the negative x, then that's negative. Is mass times centripetal acceleration, which is also to the left. That's where this negative comes from. Here's the magnitude of it. And so the speed is going to be RFS max, or m, and I take a square root. So I'm just taking this previous equation, negatives cancel, and solving for the speed. All right, no problem, Austin. So then I look at what I have, and I realize I'm not quite there. I do have a radius, so R is taken care of, but I don't have the mass of the car. I also don't have the size of this static frictional force. So I don't give up and try something else. I see if I can do anything with this. The thing I can do is remember um, two things, really. One is that maximum static friction is special in that it has a formula that may help us out of this. It is equal to the coefficient of static friction times normal force. We're given that coefficient, so that's probably a good sign. And so I just need to find the normal force, and then I'll know this. It doesn't necessarily help me with not knowing the mass, but it gets me a step further. So on the normal force, I look at the forces in the y direction. In this case, normal force up, weight down equals mass times y acceleration. It's not centripetal, it's not pointing towards a fixed center point. In this case, there is no y acceleration because the car is not leaving the road. The normal force is equal to the weight of the car, at least in magnitude. That's another one that's probably a good catch, is that is not always true. This right here, normal force equals weight magnitude, not always true. In fact, most times it's not. It's only if something is not accelerating up or down, no other forces are acting vertically, and the thing is not on an incline. If all three of those conditions are met, then this is true. But if any of them are not met, normal force does not equal weight. So don't be throwing that in places willy-nilly. It comes from looking at adding up all the forces in the y direction and seeing what the normal force equals out to. Anyway, I can put both of those things in right here to get that the speed is square root r. I replace maximum static friction was with the coefficient of friction times normal force, all divided by mass. Or then I can replace normal force with mg, weight, all divided by mass. And then I see, oh, all done. Because the masses cancel, I didn't need it. So the max speed is square root coefficient of friction times radius times g. And we did derive exactly that in the notes. I wouldn't fault you for just using that equation, but I can give you variants on these problems that actually don't have the same equation, but would follow almost the same process, so that you don't always just use whatever the nearest equation is and actually follow this process of seeing what the equation should be from the net forces. Okay, so that's 49, except for putting numbers in. What other questions are there?
Can you do question number 32?
Sure. Okay. Yeah, this is a good one. This one gets asked pretty much every time I throw it into one of these because it's got a lot going on, and so it lets you see a lot of different things at once. So again, if I were not given this picture, as soon as I started reading the problem, I would draw it. So if I did not have the picture, I would see I've got a log being pulled up a ramp. And so even just from seeing that much, my picture would already look almost like what's given. Log being pulled up a ramp. Then I read that it's a rope. I add a rope in. So I'm drawing my picture as I read the problem. 200-kilogram log parallel to the surface of the ramp. The ramp is inclined at 30 degrees. With respect to the horizontal, the coefficient of friction between the log and the ramp is 0.8. I might label that. And if the log is being pulled up the ramp, that is kinetic friction. Oh, it says it in the problem anyway, but it's kinetic friction. So I would be labeling this stuff as well as mass. This use theta for angles, coefficient of kinetic friction. Okay, and the log has an acceleration of 0.3 meters per second squared. If it's being pulled up the ramp, I have to assume it's accelerating up the ramp. Find the tension in the rope. Okay. So from here, I start following that process. This is, I think, pretty clearly a force related problem because it's asking about a force, a tension. And so I kick into pretty much autopilot to follow that process of draw a free body diagram, find net forces, and see where it ends up at the end of that. And so from now on, I am no longer looking at what it's asking me for. I am following the process I always follow with these. I label the forces acting on the log. One is tension. One is weight pulling down. One is normal force perpendicular to the surface. That's why it's called a normal force. And then kinetic friction is opposing the sliding of the log, so it acts down the ramp. Another kind of tip is don't confuse the actual frictional force with the coefficient of friction. They are different things. Only one of them is a force, and so only this one actually goes on a free body diagram. So that's the next step is replace the log with the dot, redraw all my forces on it. I've got tension, kinetic friction, normal force, and weight. I choose convenient axes, which is the ones that require the least components to be found. That would be FK and the tension force are parallel, since tension is parallel to the ramp, and then FK is also parallel to the ramp. And then this will be my other axis, the normal force, since that's going to be perpendicular to the surface of the ramp. The other bit is whether I call this X or I call up here X. I tend to lean towards call the direction the thing is accelerating positive X. So I would go up here. If you just prefer that the right always be positive X, that's fine too. Just be sure to account for any negatives that would come out as a result of that. Okay, now I need components for anything that's not on an axis, which in this case would be the weight vector. It's got this component along the y-axis. That's how much of the vector points along the y. I call that mgy. I'll find whether I use a sine or cosine for it in just a second. And then I could either draw my other component like this, or I could draw it down here to complete this right triangle. It's the same component, I just slid it around to put it in a spot that makes it clear what kind of trig has to happen in a second. And that's going to be my x component, so mgx. Okay, if I actually want to find them in terms of the weight mg, I need an angle. And just to recap this one last time, so you can see why I know that a certain angle is 30 degrees. If this angle over here on the left, the ramp angle is 30, well, I can see that this is a right triangle. And so this angle has got to be 60 degrees, so that all three angles, that those two and then this right angle add up to 180. And if that's 60, this axis, which the normal force is sitting on, is at 90 degrees to the surface of the ramp. And so that 60-degree angle I drew and this angle right here have to add up to 90, meaning this angle is 30 degrees. That's the one that goes over on my free body diagram. That's 30 degrees. Since mgx is opposite that angle, I use sine, mg sine theta. Mgy is adjacent to it, so I'll use mg cosine theta. Still in autopilot, still not really worried about what the problem's asking me about. I'm just going through the motions of this. Net force in the x direction. I have tension acting in the positive x direction. I have kinetic friction acting in the negative x direction. Equals mass times x acceleration. Oh, no, I am forgetting something there. I have this component right here also acting along the x direction. Drawing it down there makes it pretty easy to miss it. That's the one benefit of drawing it up here on the axis, is it reminds you that it is along the x direction. So minus mg sine of 30 degrees. That'll equals mass times x acceleration. Do the same thing in the y direction. I have the normal force acting the positive y. I have mg cosine theta acting downward, negative y direction. That all equals mass times y acceleration. Now I decide if the log is accelerating, and if so, in which directions. Looking at the picture, if it's sliding up the ramp, meaning along it, then it is not accelerating perpendicular to the ramp, meaning away from it. It has no y acceleration, ay. It doesn't have that. And so this is 0. That tells me that in this problem, Fn minus mg cosine 30 is equal to 0, or Fn equals mg cosine 30. That is a case where Fn does not equal the weight. It equals a component of the weight. I don't know if that's useful to me, but it's something I know now. Now is about where I would start wondering what the problem's asking me about. I've gotten through all the main steps of this process. Then I look back and say, it asks me about the tension. Oh, I've got an equation for tension. I wonder if I can do anything with it. So I solve for tension. It's Fk plus mg sine 30 plus mass times x acceleration. So I just moved these two terms over to the other side. And I see if I can finish this out. Well, I know the mass, it's 200 kilograms. I know the acceleration. Turns out this was ax, how much the log's accelerating along the ramp. I know g, it's 9.8 as always. The one sticking point is the kinetic friction. And so, again, I don't abandon ship. I just say, well, I'm a little bit closer. I wonder if I can do anything with that. And similar to maximum static friction, I can replace this with the coefficient of kinetic friction times normal force. So tension is kinetic normal force mg sine 30 mass times x acceleration. And I'm a step closer because I had the coefficient of kinetic friction given. So now it's just about the normal force. Only I had some nice convenient equation for that had all things I know. Oh, I do, from the first part, finding the net force in the y direction. So I'll put that in for the normal force. Coefficient of kinetic friction, replace normal force with mg cosine 30. Plus mg sine 30 plus mass times x acceleration. And I could calculate now or finally just factor out mass to save a little bit of calculating. It's mass times coefficient of kinetic friction, g cosine 30 plus g sine 30 plus the x acceleration. And then I would just put in the values it gave me up here. So 0.8, so it's 9.8. And then this is 0.3, and I know it's positive 0.3 because the log is accelerating up the ramp, which is the positive x direction as I've defined it. So whatever number that comes out to should be the number that's given in the answered part. Any questions on that one?
No, sir, except for when you get sine and cosine, like when
Mhm.
you're making the free body diagram for f and x and f and y, you said that it matters where the green arrows are because it might mess you up on finding the sine and cosine.
Mhm.
So that's the part that I'm still trying to wrap my head around.
Okay. So what I meant there is there's two standard ways to draw the components of a vector. Let me get rid of those for just a second. One is what we call the parallelogram way, which is that you think of the vector we're interested in, which in this case is the weight vector mg. Think of it as the diagonal of a parallelogram. The other two sides of that parallelogram are your components. And then the two sides that aren't usually drawn, these dotted lines, that's the other two sides of the parallelogram. So that's one way. to think about components. The other is the tip to tail way or tail to head. I think we called it tail to head in here. And that is that you draw your two components so that they add up tail to head to give the vector of interest. And I really have two ways I could do that here. I could do my y component first, and then follow that with my x component. And you see that they're adding tail to head, tail of the second at the head of the first. The other option is I do the x component first, and then I do the y component. It's the same components, I just decided to do them in a different order. And so if you're doing the parallelogram way, the very first way that I did, that's probably the hardest one to see whether you use sine or cosine with. Tail to head, either of these two that I just did, that's the easier way to see whether you use sine or cosine. Let me move this one for just a second. For the picture I've got right now, because of the way I drew these components and the fact that they're x and y components means they're perpendicular to each other, I've got a right triangle as a result. And so I can tell what's adjacent to the 30-degree angle. It's going to be this side. That's what's touching the angle. And then I can tell what's opposite the angle, which is this side. And so that's why I would use sine for it. The vector itself, the original vector, is always the hypotenuse. So you don't have to worry, wait, could that be the adjacent side? No, it's always the hypotenuse. Had I done it the other way, so I didn't draw my components this way, I drew them x and then y, that's perfectly fine, but then I don't have an angle inside this right triangle. So I might look at the 30-degree angle and say, oh, well, that means this is 60 degrees because they add up to give a right angle. In that case, I would see that this component is now opposite that angle. And so I should use sine, the mg sine of 60. And then this component, the x component, is adjacent to it. So I should use mg cosine of 60. That is equally correct to doing it with these two. It's just that I'm using the complementary angle, and that's why sine and cosine swap. So it is kind of up to you which one meshes best, which one feels the most correct, but all of them are equally correct ways to do it.
Oh, okay.
Yeah. Okay, let me see where we were in the notes. So free body diagrams, we've seen a lot of examples, so I'll breeze past that a little bit. Newton's third law. It's the one that's hardest conceptually because it doesn't sound right. It says that no matter what two things we're talking about, if one exerts a force on the other exerts a force back on the one that is the same size, just in the opposite direction. That's true whether it's me standing on the Earth is pulling on me, I'm pulling just as hard on it. It's true if you're talking about I crash into a brick wall, the force on the wall is the same as the force the wall exerts on me, or on the car, I should say. If you got a 18-wheeler and it hits, I don't know, a tricycle, that sounds particularly demented, I guess is why I thought of it. If it hits a tricycle, the force the tricycle exerts on the 18-wheeler is exactly as large as the force the 18-wheeler exerts on the tricycle. That really doesn't sound right, but it's true. The difference between the two is their accelerations, their change in velocity they experience as a result of that same force. Tricycle experiences a very large acceleration because it has a small mass. Newton's second law is what's at play there. 18-wheeler experiences a very small acceleration because it has a huge mass. In other words, it doesn't slow down hardly at all to the not to the benefit of the tricycle. So third law related questions will be about identifying these action reaction pairs and in particular not misidentifying. We've seen the normal force and weight a lot now. That's what these two forces are. Those are not an action-reaction pair. They are not equal by necessity. They're not equal by Newton's third law. They are equal by Newton's first. That in this picture, the cantaloupe happens to be at rest or in equilibrium, and so all forces on it balance. That's the only reason those forces are equal. The way we can tell the difference is third law pairs are on two different objects. These two forces are both on the cantaloupe. A third law pair would be one force is on the cantaloupe, the other force is on the table. All right. Systems are not on there unless there's just a problem where you choose to do it as a system, which is like pulley related stuff, which there could be a pulley type question on there, but you could do it with two separate free body diagrams or treat it as a system. Excuse me. Types of forces, not that first bit, just stuff like this. So we know now our bread and butter for the gravitational force is this right here. This is what shows up in every problem. This one, this version only shows up if you're dealing with much larger distances, where we're talking about like the moon and the earth, or if we're talking about something that's not the earth. So if I want to know the gravitational force between you and me, I would have to jump back to this because I don't know what my little g is or what yours is. I only know what Earth's is off the top of my head. So when it's questions like that, it has to jump back to the full law of gravitation. Tension and normal force, they're kind of together in the sense that, okay, how I kind of classify in my head forces, gravitational force is more like friction than it is like tension or normal force. Reason being, it has a formula. It has a way to calculate it from something else, in this case, the mass. Similar for friction. It has, at least for maximum friction, static, or for the kinetic friction, it has a formula. You'll notice tension and normal force don't have that. They are whatever they need to be in order for the problem to work out. They are just sort of a free thing that only gets decided based on whether your system is accelerating or what other forces are acting or things like that. And so the only way you really can ever find tension or normal force is through the usual look at the net force in the X and Y directions type stuff, similar for this problem. That's the only way we can find tensions and normal forces. And it's because they typically act as internal forces to the systems we're considering. So any of these problems are good problems to look at. All are good problems to look at because they are similar to what I would be testing on. Just I would test on slightly easier ones in those cases. The main things to remember for friction, other than what I said about the equation stuff, is friction is like normal force and tension up into a point. It can be whatever it needs to be to prevent something from sliding. But if you're told that something is on the verge of sliding, that's where this one is used. So if it's anything below that, and the homework has had stuff like this, the friction is just what it needs to be to oppose the applied force. It doesn't actually have to equal coefficient of friction times normal force. That's only true at the limit of static friction. Other catches for friction, not really. That's the main one. And then conceptually, that's kinetic friction is weaker than static is a main kind of idea for that. Circular motion. This right here is the one that gets messed up every time. Things moving in a circle, even if they're moving in a circle at constant speed, are accelerating because the direction is changing. And acceleration is a change in velocity. That could be speed or direction or both. This is the case where we finally see that it's the direction changing. The type of acceleration is called centripetal, meaning towards the center. Not away from the center, not tangent to the circle, not any other weird direction. It means towards the center. Do you remember that for the centripetal acceleration and centripetal force? you're good on the direction related stuff. The velocity is tangent to the circle. As usual, it's always tangent to the path. But for that reason, we sometimes call it the tangential velocity. So if you can remember tangential velocity, centripetal acceleration, centripetal force, you'll be able to get the directions of all three correct in any problem that asks about that. And the rest of the chapter is just applying the same procedure as usual, looking at the net force in the x and y directions, just for different types of forces being the centripetal force, being the force that acts towards a center point. Okay, that's the pretty quick recap, quote unquote quick. So other questions?
I'm trying to find a question on this centripetal force on the practice exam.
Okay. So anything, uh, 35 or after is that sort of realm.
Yeah, 51.
Okay. So this person's on a Ferris wheel. We're given their mass, and we're given the normal force on them when they ride through the lowest point. Okay, what is the magnitude of the normal force as they move through the highest point? So I think first inclination would be to say that those are equal, but there is a pretty distinct reason that that can't be true. And that is that so I'm gonna have to make one assumption here, which maybe was written in the problem and I just edited down too much. Maybe it's not explicitly stated, but it's the fact that the Ferris wheel is rotating at a constant speed. So it's not stated, but Ferris wheels tend to do that as far as I know once they get going. So I'm going to assume that that tangential velocity has the same magnitude. The tangential speed is the same no matter where we are. In that case, that means the Ferris wheel is undergoing uniform circular motion. And so as a result, so is the person sitting in any one of these cars. They're sitting in their top or bottom. Why that's relevant is if they are moving at a constant speed in a circle, they're also feeling a centripetal acceleration that has a constant value. Not a constant direction, but the magnitude of it. Because up here, it'll point towards the center. Down here, it'll also point towards the center. Writing AC, just say centripetal. And where that acceleration comes from is the net force acting on the person, which is normal force minus gravitational. Right? Gravity is pulling them down. Okay. Still sounds like maybe a little bit too open-ended. So this is where I would start thinking about free body diagrams. On the person sitting at the top and the person sitting at the bottom. Got the normal force, got their weight, and then normal force and weight. So the free body diagrams actually look identical, One thing that's not on the free body diagram, but then I can point out to myself, is that the accelerations are not identical. They point in different directions. So I would look at my net force, in this case, only in the y direction. It's normal force minus mg. And then same here. The difference comes in on the right-hand side. It's equal to mass times acceleration, but the acceleration is centripetal. For the guy on top, centripetal means downward because that's where the center point of the Ferris wheel is. So for him, I use a negative v squared over r. For the guy at the bottom, centripetal means up because that's where the center is for him, is above him. And so it's mass times positive v squared over r. R and V are the same for each because R is just the radius of the Ferris wheel, or at least up to wherever the guy's sitting. And then V, we had to assume, is a constant speed. Okay. Now we're about ready to figure this out. I'm going to simplify a little bit. So Fn minus mg equals negative mv squared over r for this one, and then Fn minus mg equals mb squared over r for the guy at the bottom. I'm told about the lowest point normal force. That means I know this one. I don't know this one up here. They're not necessarily the same. So maybe I'll add a subscript just to make that clear. This is upper, lower normal force. What I can see is that I can sort of eliminate this between the two equations. So how I would do that is from this first equation, I can write mv squared over r equals mg minus fn upper. I'm just kind of sliding this term to the left-hand side, sliding everything else to the right-hand side. For the lower portion, I can write mv squared over r equals fn lower minus mg. I have mv squared over r equals two different things. I can set those two things equal to each other since they both must equal mv squared over r. So mg minus fn upper equals fn lower minus mg, or let's see, fn upper equals 2mg minus fn lower, because I'm asked about the magnitude of the normal force when he's at the highest point. That would be fn upper. So 2 times his weight minus that lower one, which was 684 newtons. His weight I can get from his mass and gravitational acceleration if I give myself a little bit more room. His mass was 55 kilograms. And G is 9.8 meters per second squared. Let me double check that I get a positive. If I don't get a positive, I probably messed up a negative sign somewhere else. So I just want to make sure I didn't do that. That's 6 each. Okay, yeah, I get 394 newtons. Positive number, that means I didn't mix up a negative elsewhere. So when he's at the top, he is feeling a smaller normal force from his chair than when he's at the bottom. And this is just like when you're in an elevator. When you're accelerating downward, like he is when he's at the top, you feel lighter than normal. That's because the normal force is smaller than normal. When you're at the bottom, you feel heavier than normal, and that's because the normal force is larger than it usually is. You're accelerating upward. You would feel like your usual everyday weight if you were um, over here or over here. And that's because then your acceleration is to the left or right. It's not impacting your perception of your weight of vertical force. It's impacting your perception of horizontal force. Okay, that one is involved and is more difficult than what I'm necessarily expecting. I just wanted you to see it's still the same process. It just feels a little bit trickier because we've got extra negatives and subscripts and all these other things running around. All right, so that's that one.
Yeah. Those. So yeah, so for the highest point, the highest point will be that'll be Y or X, or that's why you switch it out to higher and lower instead of X and Y.
So it's still Y for both. So I'm still calling upward positive Y direction. The higher, lower, or upper, lower was just because I know these two normal forces cannot be the same as each other because there's no way that they can add to the weight of the guy to, in one case, give a downward acceleration and in the other give an upward acceleration. I can't have the same two forces just decide that they're in different directions for the net force. So it must be that since weight can't change for a person, just because he went higher up on the Ferris wheel, it must have been the normal force that's different for each location.
Oh, okay. That's positive.
Yeah, if there's any bit of this you want me to recap, let me know. And I'm happy to.
I think I got it.
Okay. Um, let's see. So, Thomas, did you happen to have any questions?
No, I'm good. Thank you.
Okay. Yep. Okay. Let me do a quick scroll through and see if there's any that I just want to go through to make sure they're clear. Um, so this is the kind where I was talking about you're going to need to take a step back to this version or M1, M2 would be kind of how we write it generically over R squared because this is not asking about the force between someone and the earth. It's asking about the force between two people. Um, I think this one's a good one to kind of be familiar with because it covers a lot of different things at once. So I'm just going to draw the free body diagram for it and then move on. But this one was in the homework, or a very similar one was. So tension acts along the rope. We've got whatever this applied force F is, and then weight. And so tension mg and F. I would choose these axes because then I just need the components for tension. I see this angle is given as theta. So they're talking about that angle. I tend to like to go for one that's based around my two axes. So either that one or this one up here. And I can just do that because if this angle is theta, this angle is theta. That's the geometry thing of alternate interior angles. Or I could have seen the right triangle where this is 30, this is 60, And so I could use the 60-degree angle as well. So that would be the free body diagram. And so this would be T sine 30. And then the vertical component is T cosine 30. And then you could take it from there to, well, where's 30 coming from? I'm sorry, theta. I don't know the angle. My brain said 30 for some reason. So generically angle theta, but you could take it from there. You have two unknowns, tension and angle theta, and you can eliminate either one or the other and then have a problem that's just solving for, say in this one, tension. All right, let me keep scrolling. Let me do this one real fast so I can just kind of recap the two different ways you can solve problems like this. Usually Atwood's machines type ones where you got two blocks on pulley, or this one's a much worse version of that, but it is also like, if you can do this one, you can do any of them. I'm not expecting you to actually be able to do one like this on the exam. So let me jump to this one because it is more like what I would explicitly expect. We're given weights. That's something worth mentioning is these are not masses. I wouldn't write M here. This is the entirety of mg. It's what I get when I multiply whatever the block's mass is by g. So I got to be a little bit careful with where I put that number. We're asked what the tension in the string is. Like usual, I don't really care what I'm being asked about in the sense that it's the same process regardless of what it is I'm being asked about. So my first step would be to draw free body diagrams for the two blocks. I'll show the way where you can consider them as one system after, but that's not going to help us find the tension in the string because it would be considered an internal force from that perspective. So for this, I've got two separate free body diagrams, one for the big block, one for the small one. I've got tension pulling up on the big block and weight pulling down. That weight has a magnitude of 350 newtons. For the little block, same thing, same tension force, so they're same magnitude. And then a weight of 250. So for the big block, I've got T minus 350 newtons equals M, I'll use a capital M for the big block. M times its acceleration in the y direction. And for the little block, it is tension minus 250 newtons equals little m times its y acceleration. And these are not necessarily the same number. I don't want to go too crazy with subscripts, but I just have to remember the first one is the acceleration of the big block. The second is the acceleration of the little block. What I can say is that the sizes of those numbers should be the same. One may be positive and one negative, but the sizes should be the same. Reason being, when I let this block go, I'm going to expect this one to go down, this one to go up. The heavier block would fall down. That means that the heavier block accelerates downward, the lighter block accelerates upward, but they're attached through the same rope. And so as long as the rope doesn't go slack anywhere, those accelerations have to have the same size because one end of the rope's covering the same distance as the other. So the only difference here is a lot like we've seen with the centripetal force stuff. I'll just label explicitly somewhere beside my free body diagram these accelerations. And then I can write this as, for the big block, T minus 350 equals mass times its acceleration is downward, so I'll say negative A. The little block, T minus 250 equals mass times positive A. same magnitude, A, but different directions, positive or negative. So to find the tension, I'm now down to these two equations, T minus 350 equals negative M little a, and then T minus 250 equals M little a. And so I need to eliminate acceleration. So I could solve for it in one and substitute it into the other. Maybe I'll do that. So this equation on the right, T minus 250 over M, the mass of the little block, is equal to the acceleration. I'll put that in right here. Big block equation. And please stop me at any point if I'm zooming through. I just know that you can always pause later, and I don't want to make it excruciating now unless there is something I need to go more detail on. So T minus 350, I'll distribute this negative to both terms in the parentheses. Big M 250 minus T over little m. And so I'll multiply both sides by little m to clear that denominator. Distribute the masses. And I'll solve for tension. So it should be an arrow. So I'll bring that over to this side and that over there. That's MT plus MT is 350 little m plus 250 big M. Factor our tension from the left-hand side. We're almost there. 350 little m, 250 big M. The tension is 350 little m plus 250 big M over little m plus big M. Okay, so that's going to be the weight of one times mass plus the weight of the other times mass over the sum of the masses. Let me see if I get something similar a slightly different way. So I'm going to answer this question from like the systems perspective now. And after I do that, unless there's other questions, I'll call it a day. So I'm gonna take this as my system. The two blocks, not the pulley, just the rope, the two blocks. We at this stage are assuming massless, frictionless pulleys anyway, so they don't really do anything interesting, but I'm just gonna look at the two blocks. Then for systems, I just think about the external forces acting on the system, which would be the weight of the big block, 350 newtons, the weight of the little block, 250 newtons. And my second law version for systems is the net force acting on the system is equal to the mass of the system times the system's acceleration. The mass of the system is just add up the masses of the two blocks. The net force acting on the system is what's aiding the acceleration minus what's hindering it, which would be little blocks pulling down big blocks pulling everything down. The little block is opposing that. So acceleration is 350 minus 250 over the sum of the masses. And if I combine that with this equation that I got from looking at the individual blocks and solve for tension, I think I should get the same equation I got before. Let's see, 350 minus 250, sum of the masses. That's what I found for acceleration. I also found this, so I can set them equal to each other. The minus 250 little mass. So 350 minus 250 times little mass. Sum of the masses is 2 minus 250. So E equals 250 plus 350 minus 250. The algebra is just it's tedious at this point, but I could get a common denominator, 250 by multiplying top and bottom by that. At this stage, you'd probably be putting in numbers anyway, so you don't have to do this mess of algebra. I just want to give kind of a generic algebra expression for this. So this term would cancel this term, and so I'll have 250 big M plus 350 little m over m plus big M. Same as over here. All right, that's a nightmare. But if you put in numbers somewhere along the way, it's probably not quite as bad. We would just have to remember that to get little m and big M, we divide 350 and 250 by G, by 9.8, so that we go from weight to mass instead of the usual mass to weight. Okay, that was a lot. Any questions on that?
So little m and big M are the labels, but are they actually the numbers? Like,
So I'm using them to represent the mass of the big block is big M, the mass of the little block is little m. To actually get what those numbers are, big M would be, so we know that weight is mass times gravitational acceleration.
mhm.
I'm going the other way here. Mass is weight divided by gravitational acceleration. So for the big block, that would be 350 over 9.8. Whatever that number is the mass of the big block. For the little block, it's 250 over 9.8.
Oh, okay. So you just store that into M. Okay.
Yes, yeah. So the more you do physics, the more you realize substituting in numbers a lot of the time can make more of a mess. This was probably a case where substituting them in might have made less of a mess, but I just like to keep things in terms of variables until the very end because for one, it lets me find algebra mistakes either easier, and for two, it lets me sort of see trends easier. Like if big N got bigger, I could see what happened a little more clearly this way than if I just have to substitute all new numbers.
Yeah, because I'm like, while you're doing this, I'm like, Jesus Christ.
Yeah. Don't mind me and all my algebra. The problem really is setting up this equation if you're looking at the system of both blocks, or setting up these equations if you're looking at the two individual blocks. Everything else besides that is algebra.
Hmm.
So the things I just circled is also where the majority of the points lie in these types of questions. Algebra it's an unnecessary, it's an unpleasant, not unnecessary. You kind of have to do it sometimes. Unpleasant side effect of the physics. But I grade on the physics. The algebra is just what you have to do to get to the final answer, and it's not weighted nearly as heavily as the setup to get there.
Okay.
Yeah.
That's
Really, I just did all that to see if I could still do it, see if my brain is still working okay. Um, any final questions on anything else?
not right now. Maybe tomorrow. I have
Okay.
more questions.
Yeah, any questions, feel free to email me. That goes to anyone over the weekend, nights. I'll get to it when I'm able to, and I will try to make that as soon as possible because when studying for exams, knowing fast is helpful. All right, well, thanks for attending. Thank you for your questions. It does help me to know what to go over. And I'll see y'all on Tuesday. But again, feel free to ask any questions in the meantime.
Okay, thank you, sir.
Mhm.